welcome back to Marx. We are happy to have the R of Marx, Renzo, talking about why a Torus action makes him a little less terrified by Hilbert schemes than before.
Right.
Why were you terrified by Hilbert schemes before?
I'm still terrified by Hilbert schemes, right? But let me start by defining Hilbert scheme, and then it'll be obvious that I should be terrified, right? So Hilb M of C2. These are the Hilbert schemes that I'm going to be talking about, right? This is a space, right, whose points parameterize ideals in the polynomial ring in two variables, C of xy, such that the dimension as a C vector space of the quotient ring mod I is equal to n. Okay, so now clearly, other than the word space, everything else I said was algebra, which is terrifying, right? So this is something that I'm terrified in the sense that this is not where my personal intuition lies. Right? It's very hard for me to imagine how an ideal as an algebraic object acquires sort of some geometric structure, right? And so this is a space that, if you ask me, like, okay, can you get an intuition of how the points are put together? You know, if you walk and you degenerate something a certain way, what happens? My first instinct is to be scared, right? And what I want to achieve in this hour is to show that if you like combinatorics, then you can actually do a lot of geometry on this space using combinatorics as a tool. And sort of the bridge, the thing that translates sort of the geometry that comes from the algebra of ideals into combinatorics, is the action of a torus. It's a group action. Okay, so that's the goal. Okay. So let me start by saying, okay, we have a definition here. Do we know at least some examples of some points of some Hilbert scheme of points? And the answer is yes, at least some examples that we can do. Right, so for example, I can look at the ideal generated by the polynomial x and y times y minus 1. Okay. And the quotient of the polynomial ring, I can see it as generated by the equivalence classes of 1 and y. So it's two-dimensional. So this is an example of an element of Hilb 2, C2. Another example is x y squared. Right? Everything I wrote here still holds. And another example is x squared and y, where now the quotient ring I can identify with a vector space generated by the equivalence class of 1 and x. And so these are three examples of 3 points in Hilb 2 of C2. Now, of course, if you're like me, you're desperately already looking for some geometric way to think about these points, and you say, okay, well, look, at least this first ideal, I'd say, okay, if I look at the set of points in C2 whose coordinates, when you plug them into any polynomial ideal, vanish, that gives me an algebraic variety, right, which is the intersection of the line x equals 0 and two lines y and y plus 1. Sorry, actually color coded differently. One is x. So one curve is the x-axis, the other curve is the two blue horizontal lines, right? And the points that satisfy all polynomial equations of this ideal are these 2 points. In fact, you can say, okay, well, great. So I can think of many points in Hilbert 2 of C2 as pairs of points in C2. So many points. Can be thought as, be very specific, unordered pairs of points in C2. Because I see 2 points, I don't know which one is the first and which one is the second. Okay. And in fact, okay, this space of unordered pairs of points in C2, right, is the symmetric quotient of C2 itself. Right? So sim 2 C2, which is C2 cross C2 mod Z1 to Z. I take pairs of points, and then I say I'm going to identify P1, comma P2 with P2, comma P1. And I always have a map from Hilbert 2C2 to the space, because look, even in this case, I can play the same game, and I say, what am I intersecting here? I'm intersecting still the y-axis, right? Now with y squared, this is kind of a double line, so chubby line. And so, well, my point of intersection is now just one point, but somehow, because this is a line with sort of multiplicity 2, I should think of this twice the point 0. 0, 0. And so I can also map this ideal to an element here, namely the image of the point 0, 0. But certainly, if I play the same game with this other ideal, I also get 0, 0. Right? So this function is not injective. And so certainly the Hilbert scheme is not some other, some fancy commutative algebra way to dress up the symmetric quotient of C2 itself. This is not just the algebraics that are out to get us and to confuse us. Okay? It's really something else. And in fact, I claim that in a sense, the algebraists are sometimes nice people, right? Because sometimes, because in this case, well, let me say something else, because let me leave it as suspense why algebraists can be nice. As a cliffhanger. And let me tell you one thing. So let me tell you something about sim 2 C2. Okay. So this is, like I said, is the quotient of C2 cross C2 mod the action that says that x1, y1, x2, y2 is equivalent to x2, y2, x1, y1. Now let me try to put the parentheses with this equivalence relation. But now I want to think of this a little bit differently. I want to change coordinates here and here. Okay. I'm going to use coordinates x tilde, which is x1 plus y1, sorry, x1 plus x2, and y tilde, which is y1 plus y2, and then x hat, which is x1 minus x2, and y hat, which is y1 minus y2. Okay, this is just a change of coordinates. Nothing of change. Linear change of coordinates, piece of cake, right? But the action now becomes, if this C2 is coordinatized with x tilde, y tilde, the action here is trivial. Because notice when you exchange x1 with x2 and y1 with y2, x tilde is sent to itself, y tilde is sent to itself. And on this copy, when you act and you switch x1 and x2, this becomes minus x hat. So this, the action is two copies of the non-trivial representation.
What do you mean by action? Action by what?
The action by, where did I write it? By the group Z mod to Z.
Ah.
Right, so this equivalence relation I can think of, sorry, I should have said it this way. There is an action of Z mod to Z where the non-trivial generator sort of swaps x1 with x2 and y1.
So minus means x hat.
X
y.
hat goes to minus x hat,
And then y hat.
and y hat goes to minus. Right, so
minus
this
for
is,
multiplication.
this is two copies of the trivial representation, and this is two copies of the non-trivial representation of Z mod to Z.
Okay.
And now, when you quotient by a trivial representation, not much happens. Okay? And when you quotient by C2 by the -1 representation on each coordinate, this is an exercise that is a lot of fun to do, but if you haven't seen it before, just believe me, and if you want, we can talk about it later. But this is a singular space. It's a cone over a conic. Okay, so this is C2 cross some cone over a conic inside C3. And so sim2 of C2, right, has a two-dimensional singular locus corresponding to this singularity of this cone times C2. Two-dimensional singular locus. Can everybody make a guess of what this singular locus might be? Yeah?
All the pairs of points that are the same.
Pairs of points that coincide, right? That's exactly true because the singular point here is the origin, and the origin consists when x1 is equal to x2 and y1 is equal to y2. So, geometers have a space that is very natural, but it's singular. And algebraists came up and say, here's a space that has a map to this space, which almost everywhere is an isomorphism, because there's a big open set of Hilbert that consists just of an ordered pairs of points. And so it matches perfectly with what happens here. But for those points that will map to the singular locus, I have more stuff. And maybe, just maybe, things get better here. In fact, let me preview. This will get better. This is, we'll see in a second that this is a smooth space. And so this is a resolution of singularity. There's a space which is almost ever isomorphic to Sim 2 C2, but sort of resolves the singularity, right? It has a three-dimensional space mapping to the two-dimensional singular locus. Okay? So how do we see that Hilbert 2 of C2 is a smooth space?
So that's Z mod 2 Z mod alpha. It's really S2, right?
It's really S2. It's really mu. So it's really S2 here,
Yeah.
and it's really mu2 here, right?
Great.
If you want,
Sounds good.
right? But yeah,
Cool.
cool.
After the change of coordinates, are you still like modding out by the equivalence relation?
Yeah, yeah. I'm still sorry. So I'm still sorry. Yeah, I'm still taking the quotient space. Thank you. I'm still taking the quotient space by the group action. Yeah. And no, nothing happens here because the group action is trivial. But here I get this singular space.
Okay.
And I mean, again, this is an exercise. This is very simple because if x goes to minus x hat and y goes to minus y hat, right? Then the invariant functions are just the quadratics, right? X hat squared, x hat y hat, and y hat squared. These are the invariant functions. And so the quotient space is the spec of the ring of the polynomial ring in the invariant functions. And you can see the quadratic relation, right? It's this times this is equal to this squared. This is a hypersurface in C3, and you can see that this was a quick note for the old students. If you're young, it's okay. This didn't make sense. But if you're old, it should make perfect sense. Okay. So to see that the Hilbert scheme is smooth, there is this characterization which I'm going to sort of black box, which is there's a description of tangent spaces to the Hilbert schemes in terms of, this is a game that often happens with moduli spaces. Right? So moduli spaces are spaces whose points corresponds to the object parameterized. And so you want this dictionary between the geometry of the moduli space and the geometry of the objects. And so many times, something that you can do is express some quantity about the geometry of the moduli space in terms of the geometry or the algebra of the objects parameterized by a given point. I mean, illustrate this in an example. So, quantity about the geometry of the Hilbert scheme, the tangent space at a point corresponding to an ideal to Hilbert and C2. Right? This is a geometric quantity about the moduli space. It's a tangent space. But you rummage a little bit around with the variant definition of what it means to be a tangent vector inside the moduli space, first order deformation of the object parameterized, and see what this means, and so on and so forth. And after a little bit of work, you will find out that there's a natural isomorphism between this tangent space and the group of homomorphism as C mod xy modules from I to C of xy on I. Let's take this as a black box. This is not at all obvious, but it's, again, the kind of thing that if you end up working in some of these fields at some point, you can do these gymnastics, right? And let me just show you how this works for one example. If I take the ideal to be x mod y squared, then, which is one of those bad points, right, in the symmetric quotients. And this is twice the origin. Then what is a tangent vector? Well, I can think of my C of xi mod I to be spanned, like I said, by 1 and y. And so to give a map from I to C minus I is sufficient to give a map on generators. I can get everything else via the fact that it's a C mod xy modular homomorphism, right? And so I get to send x wherever I want in this vector space. So A times 1 plus B times y. And I get to send y squared wherever I want. So C times 1 plus D y. So I have 4 coefficients in C that I can choose arbitrarily. Therefore, my tangent space is C to the 4th. C to the 4th is the generic dimension of the Hilbert scheme, right? Because pairs of points in C2, each point can sort of vary in a 2-dimensional family. We have a 4-dimensional space of distinct pairs of points. And now this is telling me that over these points that map to the singular locals, I still have tangent spaces of dimension 4. And so when a space for every point has tangent space of dimension equal to the generic dimension, this is exactly what it means to be smooth. Cool. Questions, comments so far? So with this part, I hope that I've motivated why, even if you're geometrically minded, you might need or want to care about this sort of algebraic objects, because it sort of improves. If you're interested just in a moduli space of pairs of unlabeled points in C2, but you want to have a slightly better structure, you want to resolve the singularity of this space, you'll find yourself working with the Hilbert scheme.
So at that point, tangent space has dimension 4.
Yeah. Yeah. And of course, I mean, there's a big leap of faith. I've showed you that at one point that map to the singular locus, the tangent space has the right dimension. Okay, but you will, of course, believe me under threat that this is true for every point that maps to the singular locus, right?
What do you mean by maps to the singular locus?
So we have a map that I just erased, the Hilbert homomorphism,
yeah,
right?
yeah, yeah.
That sends the Hilbert scheme to
To
the symmetric quotient,
yeah.
right? And I'm saying that all the points that map to the singularity of the symmetric quotient have the property that the tangent space is 4-dimensional. So the Hilbert scheme is smooth at all the points that map to the singular locus, and it's clearly smooth at all the generic points where it's an isomorphism, and it's 2 distinct points. It's really easy to describe tangent space to be 4-dimensional there. So it's a resolution of the singularities of the symmetric quotient.
So you're saying Hilbert scheme that we are looking at, that's smooth, right?
It's smooth, yeah. So this computation is, again, a way to sort of make you maybe have a little bit of an intuition to why. So I'm not proving anything in this talk, right? But I'm telling a story, right? It's why the Hilbert scheme is an example of why the Hilbert scheme is.
In the case n equals 2.
In the case n equals 2, yeah. I mean, yes, I know that you're seeing where I'm cheating, but in case n equals 2, I could choose freely this A, B, C, and D. It's actually, it's always true if the target is C2 or actually even any smooth surface. It's always true that the Hilb n of a smooth surface is a resolution of singularity of the symmetric quotient of sim n. This is no longer true if you go up in dimension. If you go up in dimension, these Hilbert schemes get arbitrarily singular.
You mean up dimension means C to the n?
Yeah.
Okay.
Or any space of high dimension. So the surface case is kind of like a special sweet spot. Okay, but I want to do C2, and I want to say, okay, now I've motivated myself to care about the Hilbert scheme of Hilbert of C2. I'm still terrified. Okay, so how do I actually do any geometry on this space? Other than like, okay, I computed that it's small. But can I describe the cohomology? Can I do intersection theory computations? And so let me start by showing, well, the tool that I want to use is the fact that the torus C star squared, right, acts on C2. And therefore, but simply by lambda 1, lambda 2 acts on x, comma y, by going to lambda 1x, lambda 2y. And therefore, it can act. I can induce an action on Hilbert. Okay, simply by have a polynomial and you act on the x and y of your polynomial with this action. You want to be careful. You might want to use the dual action if you're thinking of x and y as coordinates or points, but whatever, that goes beyond the scope of this talk, right? But does it sort of make sense? And geometrically, right, if I have 2 points, I say the point 1, 1 and the point 2, 2, right? And I act with lambda 1 equals 1 and lambda 2 equals 3, right? Then this will go to 1, 3. See, 3 goes up. And this will go to 2, 6. Right, so this is how the action is induced. You give me like a strange look. Are you preoccupied about the talk or about your prelim coming out? Sorry. Okay. This is okay? Okay, so we have this action on C2 and we get an action on the Hilbert scheme just by kind of moving around the points that are on C2, or if you want, moving around the coordinates, the formal variables x and y in your book. Okay. And what are the fixed points? Here's the question. What are the fixed points? I's that are fixed by this star, this C star. So I like to think of first of like the support of the points. If I have 2 points in a position like this, right, they're certainly not fixed, right? Because lambda 1, lambda 2 can move me around C2. Right, so it better be the case that it's going to be ideals that have to be supported just at the origin. Because the origin is the fixed point of C2 by the action of this torus. Right? And so only ideals that are supported at the origin have the hope of being fixed. Now, being supported at the origin is not enough. Because again, you might be changing the ideal when you plug in lambda 1x, lambda 2y. And this does not happen, the ideal doesn't change, if and only if this ideal is a monomial ideal. It can be generated by monomials. Okay, because when you apply lambda 1, lambda 2 to a monomial, you just rescale it. If you rescale it, it's still the same monomial in terms of being in the ideal, right? Because you've changed it by a unit, so they're still generating the same. right? So these are. And they are indexed. There's a little bit of combinatorics coming in. They're indexed by partitions of n by partitions of n. Okay, how do I associate a monomial idea to a partition? We do an example. Okay, so let's say partitions of 3. Right? What do I have? I have this. I have, oops, very tall. Moving to 1, to 1. I have okay. Am I forgetting something? Good. And so I think of these partitions, these boxes, as being placed at the corner of my lattice of monomials. And this give me the spots of the elements in the quotient by the ideal. Right? So if this is 1 y squared, right? The ideal is generated by x and y cubed. Right? So this partition is associated with the monomial ideal x, y cubed. Okay, and this one is 1 x and y. So this is the maximum ideal squared, right? X squared, x, y squared. And this is 1 x squared, y x cubed. And so this is the ideal y. Yeah.
Can I ask a question about something earlier? So
Sure.
why, you were saying that, like, it's not enough that they're only supported at the origin, they also have to be monomial.
Yeah.
Do you have an example offhand of something that's not monomial but is only supported at the origin?
Yeah. Yes.
And, like,
take
why
take
is
a
that
monomial ideal and do some sort of like change of coordinates so that so every monomial ideal is in a sense a intersection of a linear and a quadratic. You can generate a linear quadratic, right? Say for example, this is when we go back to my I went back to my to the example, right? So let's say they have x and y squared, right? This is a monomial ideal. But now change your x to an 2x plus y, for example, and your y squared to 3x plus 4y squared. This is still supported at the origin, right? Because it's a line through the origin and a double line at the origin. But now if you act with lambda 1, lambda 2, you'll get a different ideal because you're scaling these things independently.
Oh, okay.
So by changing set lambda 2 equal to 1 and changing lambda 1, you change the slope of this line. And so you're actually going to get a different idea. They're all supported at the origin, right? But it's, if you like the perspective that, again, in the HIB2, the double point, the ideal corresponding to the double points also have a tangent direction. Right? The condition that makes it fixed is that the tangent direction is along the coordinate axis. Cool. Yeah. Great. So here's some combinatorics, and here's some immediate consequence in geometry that the Euler characteristic of Hilbert n of C2 is equal to the number of partitions. Okay. That's pretty cool. right? Because, well, every time you have a torus action, or a group action in general, this decomposes the space into orbits. Orbits of a torus action are either points or they're tori, something that one can check. Algebraic tori, C stars to n less than the torus. But the other characteristic of a torus is 0. And other characteristic is additive under disjoint unions. And so all the non-trivial orbits don't contribute. The only orbits that contribute to the other characteristic are the fixed points. But the first non-trivial geometric result about the scheme that just follows from commutatorics. Okay, I want to do a little bit more. And so I want to semi-quote two powerful theorems. Okay, so the first theorem, first theorem is called the Atiyah-Bott localization theorem. And I want to paraphrase it like this. If you have a space X with a torus action T, you can know anything you want about the cohomology of X. If you know these two things. One, the cohomology of the fixed loci, and two, the normal bundle of the fixed loci. Okay. Again, you're not walking away with this talk saying, now I know the Atiyah-Bott localization, right? But the flavor of the Atiyah-Bott localization theorem is, if you really understand well the fixed loci of a torus action and their normal bundles, you go and ask Jay. He'll be happy to teach you all the gory details of the localization theorem, and you can do anything you want, right? And in our case, these are FIs are points. So cool, I know the cohomology of a point, right? And the normal bundles to a point, this is just the tangent spaces to the I. And so, cool, we also have a good understanding of tangent spaces because we can think of them as this sort of like homomorphisms from the ideal into the quotient. Okay, so we have good hope. The second theorem that I don't know how to spell the names and I don't know how to pronounce the names, but Maria, you can correct me. It's Białynicki-Birula.
Oh, I know the two names you're talking about. I don't know how to pronounce it.
Okay.
Yeah, sorry.
So, put some like bleeping over the video when I say.
We'll fix it in post.
Białynicki-Birula, whatever. I think it's two Polish people, right?
Yeah.
Polish have especially unpronounceable names, I think. And this is the following. Actually, let me put it in a more prominent space because it's a sad little corner. It's a cool theorem. Okay. So BB 2, and it says, suppose you have a space X with a one-dimensional torus action, C star, not just any torus. And I want X to be smooth, projective, with finally many fixed points. We call them xi. And then what BB tells us is that you can decompose X as a union of strata called X sub I that are all isomorphic to affine spaces C to the sum Ni. And the cohomology of X is additively generated by the closure of this strata. And further, let me tell you what these strata are. Xi is the set of all X in X.
Sorry, can I? So you're saying normal bundle?
Let me finish this statement.
Okay.
Okay, then I'll answer your question. Let me finish this theorem. The Xi is the set of all X in X such that the limit as t goes to 0 of Tx is equal to Xi. Okay, so you let the points flow by using the torus, and as t goes to 0, these points are going to flow to some fixed point, and the points that flow to a fixed point belong to that strata. This gives you the composition of the space into affine pieces, and then once you have this decomposition, you know that the cohomology is additively generated by the closure of this strata. Okay, so now while I give everybody time to digest this a little bit, I can answer your question.
So is that the normal bundle?
Mhm.
Are you saying is that the same as Ti?
So in our case, because the fixed loci are just points, the normal bundle to a point is just the whole tangent space.
Ah, okay, I see.
Yeah, that's what I said.
And then our fixed point is just monomial ideas, and then in this case we have 3 points, and then
Yeah.
And then what's the conclusion of this?
So the
What
conclusion
is
here.
hypothesis?
Let me see if I have time.
You didn't write down yet.
No, this is the end of the theorem.
What is hypothesis and conclusion?
The hypothesis is that, so if X is a space with a one-dimensional torus action, and X is smooth and projective, and has finally many fixed points that I'm calling Xi, then X is the disjoint union. Oh, sorry. I forgot an equal. X is equal to the disjoint union of this strata, Xi, that are all affine spaces. And the cohomology is freely generated by the closure of this strata. Okay? Now, for the sake of time, so P2 is a beautiful example. Of this, where you put the action T acts on X, Y, Z, and goes to X, T, Y, T squared Z. Okay? So if you want, do the exercise, and you try to, you take this action on P2, you see it has 3 fixed points, and I have to choose the 3 powers of T generically, like 3 different ones to make 3 fixed points. If you choose 2 of them to be the same, you have fixed sign, you don't want that. And then if you look at what the Xi's are, you will get a point, an affine line, and a complex plane. And so you get the usual decomposition of P2 into a point plus A1 plus A2. Okay, so this is an example of this theorem action. Now, there's a couple of problems with this theorem in our situation. The first thing is that this theorem works for target being projective, right? And because C2 is non-compact, the Hilbert scheme of C2, the Hilbert scheme of points on C2 is also non-compact, in the sense that you can imagine pairs of points on C2 running off to infinity. And as they both run off, or even just one of them runs off to infinity, then the points falls off the Hilbert scheme. Okay? So this condition is not satisfied. But that's okay, because that condition is not really super necessary. What this condition guarantees is that when you start flowing these points, they don't fall off to infinity. If the thing is projective, they have to flow somewhere, they have to flow to some fixed point. And so if you can guarantee instead that the limit as t goes to 0 of tx exists for every x in x, that's good enough. Okay? And so in our case, with the Hilbert scheme of points of C2, we need to choose a one-parameter subgroup of our n-dimensional torus. Sorry, of our two-dimensional torus. C2. And so long as you take both powers of lambda, we said lambda 1 equals t to the k1, and lambda 2 equals t to the k2, and k1 and k2 are both positive. Right? Then when you flow to t to 0, the points all get attracted to 0. Nothing gets chucked off to infinity. So this is satisfied. Okay. The other problem is, okay, this is great that this exists, but how do you find this and I? If you really want to understand what the cohomology is, you should actually know what is the dimension of your system. And so the cool thing is that finding this ni, the ingredients that you need to find this ni, is exactly the same ingredient that you need, the same information you need about the normal bundle to crank out the Atiyah-Bott localization theorem. Because if you have a fixed point in your space X, which in our case is the Hilbert scheme, right? Then essentially what you need to find out is how many directions are attractors and how many are repulsors, right? If you have a points that, along here get attracted, but along here, this is wanting to be a three-dimensional example. These are three independent directions.
Is this as t goes to 0?
Huh? This is as t goes to 0. Right? So points along this red axis are coming in, and points along these other two axes are being pushed out. Right? In this situation, you would know, okay, this is an A1, because there's a one-dimensional orbit coming in. I mean, you'd have to fill in the diagram like the PD people do everywhere else. Right? You'll see that the thing that flows in is one dimension. And so somehow all you need to know is you need to look at the tangent space. The tangent space will decompose as a direct sum of C star representations. And you need to look at those that are attractive, so those that have positive exponent. And those precisely give you the attracting direction, so the dimension of this triangle. Okay? So the last thing that I want to say is I just want to show you how we can control, how we can compute what representation of the torus are these tangent spaces of the fixed points. I'm just going to show you one example to show you what is the issue. But that will give a combinatorial format, right? So hopefully the audience will get it. Okay, and here we will see why Chris was sort of like uncomfortable when I gave that example of the tangent space in HIL 2, because it was an example that hid a very interesting feature of these things, but now this will come out. And I need to look at my notes because I want to have hope to finish in 5 minutes instead of rambling in the computation for hours. Here it is. So let's take this monomial ideal, this one right here. Oh, actually, no, I'm going to Hilbert 4. 1 x y squared. Okay, so this is a point in Hilbert 4 of C2. Okay. And the generators for this ideal are in red, x. Squared, xy, y cubed. Okay, and now tell me what the problem is. Right, now I have to give a map from the ideal to the quotient, right? So I should send x squared, xy, and y cubed, each of them to a linear combination of 1 x, y, and y squared. Right, so I get a c1 plus cxx plus cyy plus cy squared y squared, e1 plus exx plus ex squared x squared plus ey squared y squared, and f1 fx x plus fx squared x squared plus fy squared y squared. Is anybody feeling unhappy? You should be. Because what's the dimension of Hilbert 4?
12?
8.
But,
But you have 12 coefficients, right? So you're like, yeah, right? So it's 4 points in C2, each into it. So there's too many coefficients, right? So the problem is not that this is not true, but what it's not true is that all these coefficients are independent. They can choose them all independently. And why is that? Let me show you the situation. Well, I have this point right here, change color. X squared y, right? Then I can obtain it from x squared by multiplying by y, or I can obtain it by x times y by multiplying by x. And this gives me a relation between the image of x squared and the image of xy. Because the image of x squared times y mod I should be the same as the image of xy times x mod I. Okay? And so, okay, because I'm running out of time, please believe me that you can do this computation. And this knocks out some of these coefficients as C1, E1, F1, and CY. It's not that they don't exist, but they're not independent. Right? So you choose 1, 2, 3, 4, 5, 6, 7, 8.
so you write down cy squared there.
Oh, sorry. The squared is with the y, not with the cy. Sorry. I'm getting to the point where I'm running out of time. Okay, so these are not independent. Okay, but now I know that these are not independent, but these are independent. And so I can think of my tangent space as being sort of the c to the 8 generated by these 8 coefficients. And well, what are these 8 coefficients? Well, the way that I like to think of a linear function is an element of a tensor product. So for example, this xi going to, I don't know why I wrote squared here. y, f, y, y. So this thing right here, I like to write it as x, y, dual tensor y times the coefficients ey. In other words, this is a linear function that when you feed it xy, spits out ey and y.
I forgot my
Okay?
notebook for.
And so this whole linear function, I'm going to write it as the sum for each of these three terms of this dual times this coefficient times this vector.
Why we're doing that? I think-
The reason that we're doing that is because I need to control how the torus acts on each of these things. Each of these, when this is a variable coefficient, is a line, but it's also a representation of the torus. Remember, lambda 1 comma lambda 2 acts on x as lambda 1x. It acts on y as lambda 2y. And by standard representation theory nonsense, it acts on x dual with 1 over lambda 1 x dual. And it acts on y dual with 1 over lambda 1 lambda 2 y.
Now we're just choosing that to see some example, or why?
This is an example.
Okay.
Yeah, this is an example,
Okay.
right? But I'm going to conclude now by just showing, like, so what I hope you can see from this is that you could actually use this information and the fact that when you tensor representation, you just take the product of the various exponents to give this final combinatorial rule for the decomposition of a fixed locus into representation. And this will be very fast. So given a partition, now you need to write it, well, let me write it like this. Even though the convention was named, I think after partition the other way. Because for every box of the partition, the arm is the number of boxes to the right, and the leg is going to be the number of boxes strictly above. So this is the leg of somebody who's doing like a candle or a...
This is the better notation. So.
Yeah, but again, so let me say that, let me just write an example. The arms of these partitions are 1, 0, 0, 0. And the legs of these partitions are 2, 1, 0, 0. The number of boxes above, the number of boxes to the right. And finally, again, it should not be obvious, but it's just it's a tedious computation at this point, is that the decomposition, so T given of a given partition of Hilbert and C2 decomposes as a direct sum of representation. Let me call them C I L naught plus J L1, where what I mean by this is that lambda 1, lambda 2 acts on Z by lambda 1 to the I, lambda 2 to the J, Z. Right, so the I and the J are the exponents of the representation, and the L0 and L1 are just keeping track of which coordinate. Now, why do they call them L0 and L1 and lambda 1, lambda 2? Sorry. Should call them L0 and L1 and L2. This is what I wrote. Right. Actually. Yeah, let me not try to change it on the fly. And the way that you find these i's and j's is you write the partition twice. And in each partition you write arm minus 1 L0 plus leg L1, this is leg, this is arm, and arm L0 plus minus leg minus 1 arm L1. Okay, so you take these two partitions, right? And you decorate, so not these two partitions, you take two partitions and you decorate them according to this formula. Let me just show one box, right? So what thing corresponds to this? For this one you say r minus 1 is 0 minus 1, so minus L0 plus leg of L1, and the leg is 0, so that's that. That's
I'm confused. What you wrote down? ARM?
arm.
So what is that?
So the arm of a box of a partition is the number of boxes to its right. The leg of a box of partition is number of boxes above. Okay, and for each of these boxes in the partition, you can write arm minus 1 L0 plus leg L1 and arm L0 plus minus leg minus 1 L1. And these 8 sort of weights that you get are precisely the 8 irreducible representations. And so at that point, you know everything that you need to run either the Atiyah-Bott localization theorem, or if you then specialize to a one parameter subtorus, to run the BB theorem. And yes, I mean, I skipped the whole computation that makes you go from here to here, but you could see how like you know how to compute these weights, and then some clever combinatorialists just found a way to give us an arm and leg formula for this. Okay.
So that's the dimension of C, I, L, 0.
So each of these is one dimensional, and you have 2n of these because that's the dimension of the Hilbert scheme. And so 2n is twice the number of boxes in your partition.
What you wrote down? A minus 1 L0 plus what?
R minus 1 L0 plus L leg L1 for each of the boxes. And for each of the boxes, you have a number.
Yeah.
And so you have 2n different representations. All right, I'm already over time, so thank you. And if you have more questions, let people that need to run away, and then